We're going to have a little look at our physical properties of our alcohols, and then we'll move on to their chemical reactions. So physical properties, then their chemical reactions. And we'll look first of all at boiling point. And boiling point, as you know, is all to do with intermolecular forces. And what we find with alcohols is that their boiling point is much higher than sort of corresponding organic molecules due to the presence of hydrogen bonding. And as we know, which is our strongest intermolecular force? Hydrogen bonding. So if that's the strongest force that we have, and that's present in our alcohols, that wouldn't be present in halogenoalkanes, wouldn't be present in alkanes, wouldn't be present in alkenes, then our boiling point of alcohols is going to be significantly higher. Because in terms of boiling point, we're talking about overcoming these intermolecular forces in order to boil them. So you can have a look at those comparison tables. It basically compares alcohols with chloroalkanes. What's your intermolecular force with halogenoalkanes? What's the main one? Not van der Waals. Not van der Waals. Your dipole, because obviously they have that permanent dipole. Okay, so they have the permanent dipole. Halogenoalkanes have that permanent dipole.
Is this for the benefit?
What we found with halogenoalkanes is they had higher boiling points than their corresponding alkanes because of that stronger intermolecular interaction, the dipole-dipole. But what we've got with alcohols now is, with our alcohols, we have a group that is able to hydrogen bond. Okay, so those alcohol molecules can hydrogen bond to each other, so it's going to take even more energy to overcome them. So you can see alcohols compared to halogenoalkanes, where their main intermolecular force is dipole-dipole, and then alcohols compared to alkanes, their main intermolecular force is?
Alkanes?
Yeah. Van der Waals. Yeah. So obviously it's going to be higher than that. So let's have a look and see if we can just represent that by. Does anybody know what the boiling point of ethanol is?
Yeah.
Great, tell me.
132.
You're wrong. It's not 132.
7 degrees.
No, higher. Oh, actually? Oh, because you read that from the previous page. Yeah, I was going to go for 78 degrees C. My goodness, that's impressive. And why did she keep quiet that whole time if she knew that? So let's draw the hydrogen bonding in ethanol. Okay, so we're just going to draw it straight for now because it's easier to draw. So there's a molecule of ethanol. Okay, and what does hydrogen bonding arise from? What does oxygen have that means it can hydrogen bond to another? Lone pairs, great. So I know this is wrong, don't worry. I know this is wrong. We're going to draw the correct shape in a minute, but just to help us see the hydrogen bonding, we're going to show the lone pairs, one above and one below. Okay, but I know that's wrong, don't worry. I haven't completely lost my mind. And so what that can do is it can use this lone pair to hydrogen bond to a hydrogen, and it can also use this lone pair to hydrogen bond to another hydrogen. A hydrogen that is connected to NORF. Yeah, perfect. Okay, and so what we've got here is our hydrogen. So we're kind of going to draw our ethanol molecule, but in reverse to what we've just drawn it. Okay, but also what does this oxygen then have? It has lone pairs as well. And so what it can do, bond to
The hydrogen on the original.
Yeah, brilliant. It can.
A stronger bond.
Yeah, so it's like locked in, but it can also use that lone pair to hydrogen bond to one below it.
And then you get dirty chain.
Yeah. So great. If you could draw that in, and then to the right of it, we'll draw the actual shape of it.
Oh yeah, because it's the water bent.
Yes. Well, the hydroxyl group is bent. Brilliant. In your exams, make sure you label your hydrogen bond. So either do a little key at the side or just an arrow from that and say hydrogen bond.
Oh,
Oh, I didn't even write my book.
You have to
Yes,
label them.
always label. No labels, no marks.
Goodness.
Let's look at the actual shape of alcohols. So as we know, the two lone pairs on oxygen mean that it's a bent shape around the oxygen, just like in water. So with water, we have two bonding pairs and two lone pairs. And that corresponds to a bent shape. In our alcohols also have two lone pairs on the oxygen, so our alcohols are bent around that hydroxyl group, so it's sort of connected to the carbon chain, and then got the hydrogens kind of going off like that. And so for ethanol, or just our general alcohol, if you're happy enough, we will use the formula of R to represent our alkyl chain, and then our hydroxyl group. Okay, so to show our hydrogen bonding in the proper shape that it is, we've got our R, which is our carbon chain, and then our hydroxyl group, and then we've got another alcohol group that's lined up next to it. And so what the hydrogen bonding then does, if we draw our lone pairs on our oxygen, so 2 on that one, and 2 on that one, what that does is it hydrogen bonds to this hydrogen. So it's kind of diagonal because of the position of your lone pairs. So the way we drew it in the previous diagram, we had drawn the lone pairs just to aid our diagram. But this is the actual shape of them. Because those lone pairs are kind of pointing out, it'll go diagonally up like that. So we've got our delta negative oxygen, our delta positive hydrogen.
And then at the side, do we just do R represent R equals?
Yeah, you can do R equals your alkyl chain is the proper, or alkyl group.
And is that just like, alkyl group could be like CH2 or C2H4 or just anything?
Yeah, it'll be CH3 is your methyl, C2H5 is your ethyl, C3H7 is your propyl. So it's basically, if you want to put in brackets, your carbon chain. Okay, and then obviously this water could, or this oxygen could hydrogen bond to another alcohol that way. But that's kind of how they arrange themselves in reality. Okay, so another property of alcohols is that they're soluble in water. And the reason that they're soluble in water is because they can, well, first of all, they're polar. And we find that polar substances dissolve in water because water is polar and like dissolves like. But also because alcohols can go one step further. They can do what to water molecules?
Hydrogen bond.
They can hydrogen bond to water molecules. So it's all about the hydrogen bonding with alcohols. Now, you see this definition that's in brackets, that's one of your CA definitions. So we say that alcohols are miscible with water. So obviously alcohols tend to be liquids. And so we describe, what does miscible mean?
Mixed with water.
Yeah, so that they're, well, not necessarily with water, they're just two liquids that can mix. So yes, our alcohol will dissolve in the water, but we also just talk about that mixing as well. So it just says there, liquids which mix in all proportions, i.e. form a single layer. So
it's
not
like oil and water.
exactly, these were the exact words that were going to come out of my mouth. Oil and water, they would form two layers, okay? Whereas alcohols and water, they form just one layer because they fully mix, okay? And it's because of our ability of our alcohols to hydrogen bond to water. So let's draw our alcohol again and how it hydrogen bonds to water. So if we draw our alcohol, our lone pairs and our oxygen, which are going to be doing the hydrogen bonding. So that's our delta negative oxygen, or delta positive hydrogen. And then we'll draw a couple of water molecules to that. So our oxygen can hydrogen bond to a water molecule out here. But also our water can hydrogen bond to our ethanol. So if we have a random water molecule here, kind of in the same orientation as our alcohol, well, what we need for hydrogen bonding is an electronegative atom that's connected to a hydrogen that has a lone pair of electrons. Okay, pink. So the oxygen of our water molecule can also then hydrogen bond to the hydrogen of our hydroxyl group of our alcohol. So we've got our delta negative oxygen, our delta positive hydrogens. So we can see essentially what we've got here, kind of on the left, is our alcohol hydrogen bonding to a water molecule. And on the right hand side of it, we've got a water molecule hydrogen bonding to our alcohol.
Could the oxygen not bond to water?
Yeah, it could. Okay. That's fine. So if you want to draw another one, just to keep our diagram simple and neat. Yeah. So this goes on and on and on. So let's have a look at how we produce alcohols, our methods of producing alcohols. 2 of these we've already met. The third is fermentation, which you have probably met at GCSE, and you'll know that's how we get our alcoholic drinks. So one of them is from halogenoalkanes, so it's one of our reactions of halogenoalkanes, and that's the hydrolysis using our alkaline catalyst, or sodium hydroxide. So I was about to ask you what type of reaction this is, but it's alkaline hydrolysis. So, say for example, if we want to make ethanol, we would just take the corresponding halogenoalkane. So, give me an example of something I could use. So, I want to make ethanol. What halogenoalkane do you think I need to start with? Pardon? Bromoethane. Perfect. What's another one I could use? Chloroethane, yeah, as long as it's something ethane. Okay, so for your equation, you would write that's bromoethane plus sodium hydroxide would give us ethanol.
Would fluoroethane still work because it's stronger?
That's the slowest hydrolysis. No, that bond is very strong, so the hydrolysis is difficult with that. So we don't really use that. This type of reaction is, I said it.
Neutralization.
Nope. Alkaline hydrolysis. And what mechanism is this?
I refuse to answer.
What mechanism is this?
It's going to be addition.
A substitution, good, yeah. So we've got our hydroxyl group, our bromine group being substituted for a hydroxyl group, good. So the second word is substitution. What's the first word? Nope. Nucleophilic. So it's either going to be electrophilic or nucleophilic, and then either substitution or addition. Obviously, you also have your free radical substitution, that sort of thing. But okay, so nucleophilic substitution, and remember we looked at depending on the structure of your halogenoalkane, it could be SN1 or SN2. But all I'm looking for there is that you've got nucleophilic substitution either way. All right, so turn over the page and we've got our industrial production of ethanol. So one of those being fermentation of sugars, and that's how you get alcoholic drinks, is by, obviously we don't want like any ethene in there. So we take our glucose, it's all biology I feel, glucose from fruit, and we ferment them using enzymes from yeast, and they produce ethanol and carbon dioxide. Is your equation there? No, it's not. Fermentation. Biologists, can you tell me? What's the formula of sugar? Glucose? Great. So that breaks down to give me, the enzymes break it down to give it ethanol and carbon dioxide. What do I need to do to balance that? And then So the enzymes in yeast break the sugars in our fruit down into ethanol and carbon dioxide. There's just a little note there about when you are making alcoholic drinks, you put a one-way valve in so that the carbon dioxide can release, otherwise your pressure is going to build up in your flask and it will just burst. But we also need to make sure that oxygen doesn't get in. So this needs to be an anaerobic reaction. Means no oxygen. Okay, second way we do this industrially, but not for alcoholic drinks, is the reaction of ethene with steam. And we looked at this in our alkane. Okay, so can you remember our conditions for this without reading them? So we need 300 degrees and 60 atmospheres. And a silica support catalyst of H3PO4, phosphoric acid. And so your equation is ethene, which is
C2H4.
And what state is it in? Ethene is a gas. Steam is water in what form? Fuel. And so what our water does, it adds across the double bond and we get C2H5OH. Okay. So if you just want to write underneath this is ethene, steam, ethanol. So all of those apart from fermentation we've met before in our previous topics, so we're starting to see the links in between the two. Right, after that, it just talks about the uses of ethanol in particular, alcohols, but in general, ethanol. So we can use it as a fuel, and your advantages are listed there. It's a clean fuel because it doesn't have sulfur impurities, so it doesn't release sulfur dioxide, so it doesn't contribute to, what does sulfur dioxide do? Acid rain, so it doesn't contribute to that. If we get our ethanol from fermentation, we get it from sugarcane, which is obviously renewable. We can just plant some more sugar plants. It releases a lot of energy, loads of advantages for ethanol there. We can also use it as a solvent, and it's used in cosmetics, toiletries, glues, paints and inks. And finally then our alcoholic drinks, and as we said they're made by fermentation. So for example beer, fermentation of barley, which gives us a weak solution of ethanol, about 3%, that's why beer has a low alcohol content. Wine is fermentation of grapes, and that gives us a slightly stronger solution of ethanol, about 13%, and spirits like vodka and rum, they have to be made by fractional distillation, because with our fermentation, basically when you would have learned this at GCSE, I think when it gets to about 15%, the ethanol kills the yeast, and so it doesn't, the fermentation stops, and you'll see that by your carbon dioxide bubbles will stop. Okay, so that's when the ethanol concentration has got so high that it's killed the yeast. I think that's about 15%, and things like vodka maybe 40%.
I think you can get one for pretty well, absence is like 80-90 grand.
Okay, well that's crazy. So if we want anything higher than 15%, we need to take what we get from fermentation, put it in a fractional distiller and take some water off it. So obviously you've got a higher concentration of alcohol. So we can't produce things like vodka and rum just from fermentation. We have to take what we get from fermentation and then distill it to get it into a higher concentration. You do need to know this social responsibility of drinking alcohol. You do actually need to know this. You need to know what problems alcohol can give. So obviously it can have severe health problems if you overuse alcohol. And they're all there, aren't they? So heart disease, cirrhosis of your liver and brain damage. So very severe problems. Obviously alcohol is addictive, and that can lead to a lot of social problems, a lot of family problems, a lot of family breakdowns. And then your road accidents as well. So obviously the advice is don't drink and drive. Very simple. There obviously is your safe limits, your units of alcohol in your blood that you are legally allowed before you're over the limit to be driving. But obviously,
You need to know the advantages as well.
well, there's an advantage there. Many adults socialise by going out with friends for a drink. It's enjoyable, but it has serious consequences. So you do need to know that social responsibility of it. And that social responsibility is to, yes, enjoy it, but know your limits and know how not to get in a car when you're driving. Your units as well, your units of alcohol, that is in your specification. If you look on the front page. So you do need to know those units. The most important one there is your, like for men, it's 21 units per week. For women, it's 14 units per week. That's the most important one. The other ones...
What happens if you consume more than that, then you get all your diseases and stuff?
Yeah, over long term. Obviously, like...
If you did it like 1 week on holidays, you see.
I would not encourage that. Especially when you're 16.
Oh,
That's just telling them. Yeah, of course.
I don't drink.
So our reactions of our alcohols then, which takes up the majority of the rest of our topic. And the first reaction type, like with all our organic compounds, although we didn't look at with halogenoalkanes, that's because they release chlorine, bromine and all, and that's not good. But we can combust alcohols. So what is combustion? The reaction of our alcohol with oxygen. Good. And what are our products going to be?
Carbon dioxide.
And water. Great. So let's write the equation in here of ethanol burning, because as I was saying earlier, this can be used as a fuel, and burning fuel is just combustion. So we've got our ethanol reacting with water, or oxygen, sorry, to give us carbon dioxide and water. Go balance. Just make sure to count your oxygen from your ethanol as well. So our balancing numbers, when you work them out, are 3, 2 and 3. So just be careful when you're balancing these to make sure you count this oxygen that's in ethanol, which you wouldn't have had to do before for your alkanes and your alkenes. Okay. No, what we didn't mention in our advantages before was this idea of a cleaner flame in terms of our carbon content. So we learnt that alkenes give a more sooty orange flame. Why was that?
Because their carbon content
Is
quite high.
Is higher than, so think about ethane versus ethene. Okay, your ratio of carbon to hydrogen in ethane is
1 to 3.
Thank you, and in ethene
1 to 2.
is 1 to 2. So you can see that our carbon content is higher in alkenes. Okay, and so that gives the more carbon content there is in a fuel, the more sooty it is. Okay, but with alcohols, because of our oxygen, we've got a lower carbon content, and so alcohols burn with a nice clean blue flame. Okay, and then you've got your advantages of ethanol as a fuel again, and then just below that the note that if you if you have a limited supply of oxygen, then you'll have incomplete combustion, which gives you what as an alternative product? Carbon monoxide and water, and sometimes you actually even get a little bit of carbon as well, which appears as like soot. So our next type of reactions of our alcohols is oxidation reactions, and this is a major reaction of our alcohol. And a really important aspect of this type of reaction is that we use it to distinguish between primary, secondary and tertiary alcohols, and this is something that comes up on the practical exam all the time. So we use it to distinguish between primary, secondary and tertiary alcohols. We looked at the difference between the structure of our alcohols yesterday. Okay. The reagent that we use is something called acidified potassium dichromate, and the acidified part is important. Acidified potassium dichromate, dichromate 6. Okay, what do you think that 6 applies to?
The oxidation number of the chromium.
Good, the oxidation number of the chromium. Yeah, good. So our formula of it is, which is what I tend to remember more than that name, is K2Cr2O7. So we've got 2 atoms of potassium, 2 atoms of chromium, 7 of oxygen, but it has to be acidified. And when it is oxidized, or when it oxidizes an alcohol, we go from orange. The potassium dichromate is naturally orange, but when it oxidizes an alcohol, it goes from orange to green. Okay, and when oxidation doesn't happen, it just stays orange. Okay, and that's how we use it to distinguish between primary, secondary and tertiary alcohols. Okay, and the reason that is because primary and secondary alcohols oxidize very easily, but tertiary alcohols, well, they can oxidize under very strong conditions, but not with normal oxidation, not normal like room temperature. Primary acidified potassium dichromate will oxidize primary and secondary alcohols at room temperature, so just in the lab. If we added a bit of potassium dichromate to ethanol, it would oxidize and change from orange to green. But if we added it to a tertiary alcohol, it wouldn't change because the alcohol wouldn't be oxidized, and that's because of its structure. So if we look to see what primary, secondary and tertiary alcohols are oxidized to, primary alcohols are easily oxidized to something called aldehydes. So primary alcohols are oxidized to aldehydes, and then they're oxidized further to carboxylic acids. So firstly the aldehydes, then to carboxylic acids. Secondary alcohols are oxidized to an organic molecule called a ketone. So secondary alcohols are oxidized to ketones. And then tertiary alcohols we see don't oxidize under normal conditions. And a good way to remember this is PACSK. So PAC-SK and a small e. So that's, what does the P stand for? Primary alcohols. Go to aldehydes. And then to carboxylic acids. S stands for secondary alcohols. Go to ketones. And so you've got a picture of Pac-Man on skis.